right, well, thanks everybody for joining today. I have the pleasure of going after a great presenter earlier, so we'll see how I do. But just to tell you guys a quick story that's kind of a HVAC joke to lead it off. I was in Oklahoma City last December, and I was meeting with a guy who used to have a cooling tower company. And he started it up from scratch, and his son just graduated college. So he hired a bunch of kids that his son knew that just graduated. They weren't business majors, they were like general education majors, and he hired them to be their sales force. No engineering background or anything. And he signed one of them up to do a presentation on the cooling tower product at an event similar to this. So the kid's going, well, I know nothing about cooling towers. How am I going to present about this? And the guy goes, hey, just don't worry about it. It's, this was back in the 70s, 80s. Nobody could look stuff up on their phone. He goes, if you have questions that you can't answer, you just say, that's a really good question. Can I take your number and I'll get back to you? So he goes and presents, and he calls the guy after, and he goes, so how'd the presentation go? And the guy goes, it started well, but it didn't go too well at the end. And he goes, well, what happened? And he goes, well, one of the guys raised their hands and asked, what tonnages are your cooling towers in? And I go, okay, well, what'd you say? And he goes, well, I told the guy, I don't know how much they weigh, but I'll have to get back to you. All right, so, let's see. Okay, so this is what we're going to talk about today. So just a quick overview of who we are, one slide. Then we'll get into the definition of what an EC motor is. I'm going to compare the lifetime of an EC motor versus an AC motor and a VFD, replacing EC motors versus replacing AC VFD motors, brake horsepower versus kilowatt. EC motors always give you a kilowatt. AC motors are always going to give you a brake horsepower with the fan. So how do we compare those two, contrast them, and then go through some EC myths. So some myths that are in the market. It was actually, all the myths that I point out were actually from a brochure from a AC motor manufacturer about some of the issues EC motors have, and we'll go through those. All right, so just a real quick update. EBM Pabst is a 2.5 billion euro company headquartered in Germany with production sites around the world. The one that's the most interesting and the newest is the production facility in Johnson City, actually Telford, Tennessee. So we are actually producing EC motors in the United States of America. Yeah. So what does EC stand for? EC is electronically commutated. So it's just a brushless DC motor. So a computer fan that you have in your laptop or in a server tray is technically an EC motor. But the ones we're talking about, obviously, are much larger. But when it's brushless DC, what it's actually doing is it's taking in that three-phase, 460-volt power and converting it to a higher voltage DC. So the motor is actually running on DC. And it's an external rotor motor. So what that means is, so this yellow rotor cup around the outside of it is what's actually rotating. So it's not a shaft coming out through the middle. You're actually attaching a wheel to the outside shell of the motor, and that's what rotates. The reason that's nice, cover it more, is gives you a little more compact space in that air handler. So you can see it's not taking up a lot of space in this sample unit behind us that they built up in a very quick time over lunch. And it's a brushless DC motor, as I mentioned, a permanent magnet motor. So the EC motors are permanent magnet motors, if you see that lots of times on specs. It has the integrated commutation electronics, PID functionality. Everything's factory balanced before it gets sent to you. So every single motor gets factory balanced, gets factory tested. So there's no way to get like a fan dead on arrival or anything. It runs through a whole bunch of tests all the wiring contacts, does 100% speed, 40% speed, has an alarm relay built in. It has locked rotor protection. So what it actually does when the rotor's locked on our fan is it senses the rotor's locked, tries to start, sends out the alarm that, hey, I can't start, it's locked, and then we'll wait 3 seconds and try again. And it'll just keep doing this until the alarm clears. What's nice is with the AC motor, what you do is you end up, the rotor's locked, and it just keeps on torquing up and heating that motor and damaging that motor because you're adding heat now into the bearing system, adding it into the windings until it actually reaches a thermal trip, and that's what actually stops the motor from continuing to try and torque up. So with the EC motor, you never generate that extra power. It has soft start, no brownouts, short circuit protection. There's no SCCR rating needed with an EC motor. So because there's no wiring between the control electronics and the actual motor itself. You don't need to worry about SCCR. EMI, RFI protection standard, over temperature of the electronics in the motor standard, and they integrate very nicely with the BMS, DCIM, with that single point contact that Q-PAC has. So just to show a visual of kind of what's included within the EC fan assembly, you have the motor filters, you have the fan and wheel and motor, you have the VFD, inverter, line filters, EMC filters. All of that's in the EC motor package. So this is saving you weight and room in your air handler. Some other nice features, because it's that DC, brushless DC motor, no slip losses. You don't have to worry about synchronous speeds or anything like that. Up to 95% motor efficiency. You get real precise motor control and feedback. You could actually put this in a closed loop speed control, and you could tell it, I want you to run at 1,495 RPM, and it'll run at that exact RPM, constantly monitoring itself, making sure that it's holding. Identical performance at 50 and 60 hertz. Standby power is less than 3 watts, and there's lots of different ways to control it. So you could use 4 to 20 milliamps, 0 to 10, Modbus, BACnet, lots of options. So this is a very, very graphical slide to show the space savings, but I'm sure you guys can kind of already see from the unit behind that's a real unit. EC motors are much more compact in an air handler, and they're also a lot less weight in an air handler. So you're saving not only like 1 or 2 people can lift these up, install them, it's just a lot of time and savings in the space and labor. So things that aren't needed with an EC motor, you don't need shielded cabling, you don't need a sine filter, you don't need motor protection, don't need shaft grounding kits. The motor itself has an isolated shaft, so you don't have to worry about shaft grounding, and you don't need a variable frequency drive. So the other thing about it, it's simple and safe. You don't have to worry about buying a VFD from one person, a wheel from somebody else, a motor from somebody else, and it not pairing, not matching well. Okay, so getting into the lifetime comparison. We talk about lifetime of EC motors. We're normally talking about the L10. So L10 means this is the amount of hours that 10% of the sample field would fail. So 90% would still be running, 10% would have failed at this time. And we get these numbers from our suppliers, from testing. We're able to determine the different variables that go into this calculation. So we find it in air handler with a typical air handling operating curve of where it's, what speeds it's operating at, what temperatures. We get a lifetime of approximately 100,000 L10, so 100,000 hours for the L10. It's about 11.4 years. So the other thing, as I mentioned, 100% of the fans are dynamically balanced, 100% are end-of-line tested, and once installed, they're maintenance-free. So there's no greasing the bearings or anything that you have to do with the fans. Typical life of a VFD, about 7 to 12 years. This is what they'll advertise on the manufacturer's websites. Thank you. The typical life of a 5-horsepower AC induction motor is 12 to 17 years, they say. But that's based on nameplate, voltage, and frequency. The reason that's key is the second you pair it with a VFD, you're no longer running it at the nameplate frequency. So that life is going to decrease. The life is also going to decrease if it's not assembled and balanced properly, if there's no shaft grounding kit when you needed a shaft grounding kit, proper shielded cabling isn't used, and if the VFD isn't programmed correctly for that motor. So replacing EC external rotor motors versus replacing an AC VFD solution. So this is the perception. Because EC motors, you need to replace the entire assembly, it's going to be a lot of additional cost. EC motors have a long lead time, so now you have additional downtime of your unit. And this is one that's just kind of a design practice, right? With an AC motor and a fan wall, you put backdraft dampers in there just in case one fan fails. It's not going to get that fan spinning backwards, and you don't have any issues with recirculation or the fan generating power. And the perception on replacing AC motors. Standard induction motors are easy to get, commonly stocked. You can replace the motor only and leave the existing wheel and VFD, and that's cost savings, and it's a simple installation. So this is what you think happens when an AC motor fails. You have the motor running, and now the motor's failed. You remove the motor, and the existing VFD and impeller are left that you're going to reinstall on the new motor. Put the new motor there. Everything's running happy again. You completed your installation. The reality, though, is the motor fails. You remove the motor. Because lots of times, as we mentioned before, these could be big motors. You'd have to take this apart piece by piece to get it through that small door that we were talking about. The building might have been built around the air handler that this motor's in. So it could be a real challenge to get this motor out. You might need a crane, a little jib crane in the unit. And then the existing VFD and impeller are still going to be left there. So you replace the motor, but now there's a problem. The impeller and the motor are no longer balanced together. So if you don't get a balancer on site to actually balance that, that motor is going to be a problem. And we all know most people are not getting a balancer on site when they're putting it back into service. They're just getting it up and running as fast as possible. If you do get a balancer on site, it's a lot of extra money, it's extra downtime, it's expensive to get somebody that's certified to balance these to actually come out to the site. That's a lot of downtime and it's a lot of extra cash. Also, as I showed before, the VFD has a lifetime that's a little shorter than the motor. So when that first motor fails, the best practice lots of times would actually be to replace the VFD as well, because that way you don't want to make another service trip in another 2 months or however it is. So that's additional downtime, additional programming, additional cost. So what happens when an EC motor fails? EC motor fails, you remove it. Due to having the array of fans, you still are getting some airflow. As Matt mentioned before, lots of times you're designing it with N+1, which means you're still getting the full airflow through that unit. So no concerns about continuing the cooling of that space. If it's a hospital, you don't have to worry about any rooms getting shut down or any equipment being damaged. Then the EC fan is replaced. The assembly is already pre-balanced, so you don't have to worry about it. It's already programmed. You don't have to do any programming. And for most sizes, the unit can be replaced without a crane. Fits in an elevator. 1 or 2 guys can lift it up, as we saw before. These are much, much smaller products. So the reality on replacing EC motors is the entire assembly lots of times is going to be cheaper than replacing the motor only when you factor in all the extra costs of what you have to do. So the extra downtime of the unit, if you actually get a balancer out there, lead time risk can be mitigated by choosing standard parts as well as by localized production. So having production in America now means that the lead time on those parts is very, very short. And lots of times what people do too is, hey, if I did a big building with 5 air handlers, I chose the same fan on all 5 of those, and the building owner just keeps a fan in stock. So that way, if they do have a fan go down, they can replace it with the one fan that they have in stock and reorder that one fan. Another thing is, I talked about the backdraft damper before. So if you have an array of fans and one of them fails, that fan is going to start spinning backwards. When you have an AC motor, that fan generates power, and if you have it hooked up to the same VFD as the other 3 fans, it's going to feed power back into that VFD and could damage the VFD. And you actually now have to replace a VFD, which is why you lots of times are including a backdraft damper to prevent that. You're actually preventing that recirculation, preventing that generation. With our EC fan, what it actually does when it fails, still spins backwards, still generates power, but it actually is smart enough to power its own electronics, realize it's spinning backwards, and then there's an electronic brake inside of it, and it dissipates all the energy by applying that brake to the fan, and it'll just keep doing that. So it never actually allows the energy to escape the fan itself. The reality, I'm replacing AC motors. AC motors can be very heavy, difficult to maneuver. Lots of units are actually built into the building. The walls were poured after or put up after, and now you actually might have to take out a wall in order to replace this AC motor. After replacing the AC motor, if the impeller and motor aren't rebalanced together, that first fan that failed is almost always going to be your second fan that fails. And since most impellers aren't getting rebalanced, that's the first fan that fails, this is the second fan that fails. And the best business practice is also to replace the AC motor with the VFD, just because the VFD life is right in line with the life of the AC motor. So to give some comparisons on weight, our 11-inch, 1.5 horsepower motor weighs about 21.6 pounds. Typical AC motor assembly, not including a VFD, is about 35 pounds. The difference in that is about a bowling ball. So that's the amount of weight you're pulling out of that unit. The difference between a 12-inch fan with a 5 horsepower motor, now you're talking about if a hurricane's coming, it's that bag of sand that you're putting down to keep the water out. So we get larger, 5 horsepower motor, 16-inch fan. That's about the weight of a Lazy Boy recliner. So if you have 4 of these in a unit, you're pulling out 4 Lazy Boy recliners weights worth from that unit. And a 7.5 horsepower, 18-inch fan, now you're talking about a fiberglass canoe. Anybody that's ever dragged a canoe to the beach knows it's not light. This is the weight that you're saving somebody in your unit. It's the amount of extra extra manpower that's not needed to replace this unit. All right, so comparing kilowatt to brake horsepower. So when we give you a kilowatt, any of the EC fan manufacturers, they'll give you a kilowatt. It's for everything you see in the picture there. So it is the actual electric input power required to spin that whole assembly, including electronics, including wheel, including motor. When you get a brake horsepower, that is the power needed to spin the wheel at that operating point. So it doesn't factor in any belt drive, AC motor, any filtering that you have in any VFD. So the reason that's important is you cannot just take a brake horsepower, convert it to kilowatt, and say, oh, that's my comparison. So this was actually an example, 40,000 CFM unit, 12-fan unit. They're using a premium efficiency 7.5 horsepower motor. They converted their brake horsepower directly to kilowatt and vice versa. They took our kilowatt, converted it to horsepower, compared the two and said, hey, your fans, you told me the EC fans are more efficient, and they're actually not, based on this. So what I had to tell the guy was, hey, look, you're not factoring in the motor, the electronics, and everything else. And there's another problem. So say that you take a motor that's 93% efficient and a drive that's 95% efficient. That's their peak efficiencies. So they're not all going to line up on the same exact spot. Unfortunately, that's a little tougher to figure out exactly how to compare those two. But the bottom line in this case was we just took a 95% efficient motor, 93% efficient drive, gave the drive and motor all the benefit of the doubt, and it still turned out the EC motor was more efficient when you factored it in. So that's just something you got to keep in mind when looking at brake horsepower. It does not include motor and drive. All right, so this one's about EC motors at part load versus AC motors at part load. So that other one was talking about kind of the full efficiency of the motor. But one big advantage of an EC motor is it holds its efficiency much better than an AC motor with a VFD. So this is some measured data that we did on an airflow chamber of our fan going down to 50% speed. What we found at 50% speed, our motor was still 75.17% efficient. This included the wheel on it. This was the total efficiency, but it was just the motor drive efficiency, not the wheel included. So 75.17% for the motor and drive. This is at 50% speed, based on actual measured test data. And we did a 6 kilowatt fan, which is about 7.5 horsepower motor. So to give a generous comparison, we compared a 6 kilowatt fan, which is 7.5 horsepower, to a 10 horsepower motor. 10 horsepower premium efficiency motors have a higher efficiency than 7.5 horsepower. We also considered 50% speed again. But one thing to keep in mind is power is cubic to the speed of the fan. So 50% speed is not 50% load. 50% speed is actually 12.5% load. And also another thing to keep in mind is if you have a brake horsepower of 7.4, you're not selecting a 7.5 horsepower motor, right? You're going to go up a size. You're going to go to a 10 horsepower motor, maybe even higher sometimes, just to make sure that you have enough headroom and have the torque. So 50% speed is actually even less than 12.5% load. So these are some energy.gov curves that I found on their website of how premium efficiency AC motors operate. So 12.5% load, the 10 horsepower motor is 68% efficient. So that does not include the drive. So we already have a 7% energy savings at 50% speed just based on pure motor technology alone. But now if we factor in the VFD and go to that 10 horsepower and 12.5% load, we're going to see is the EC motor just on motor technology alone at 50% speed is gaining 19% energy efficiency. Lots of times, units are designed for the hottest day of the year, and most of the time it's operating at a part load. So this is why this is so important. Most of its operating hours are not going to be at 100%. This continues to grow as you go down in speed. EC motors can get down to 10% speed, and even a little lower, actually, whereas an AC VFD, normally you're going to be around 30, 35% speed. Yeah, and another point that I made there is EC motors, all of the EC motor manufacturers are also aerodynamics experts. So all three of us are German companies. We're across the valley from each other. We're all three here today. All of us take very high pride in our aerodynamic design as well. And what you get with ours is you get a package of a fan wheel that's actually designed perfectly for that motor combination. Each motor's wound specifically for the fan wheel, so you're getting peak efficiencies. So based on technology, it's 19% savings, but based on actual wheel design and getting a more optimized wheel, you're talking even substantially higher than the 19%. And then there's the method of, instead of speed control, staging fans on and off. So one thing I want to say is I talked about how power is cubic to the speed of the fan, which means power, excess power is going into the bearings, it's heat, and that's going to shorten the life of your product. So if you could speed control the fan down a little bit, the life actually goes up exponentially. So that's one thing to keep in mind is when you're turning on and off fans, if you have lots of fans running, say you wanted 50% airflow and you turned off half the fans are going to be running at 100% speed. You're actually going to be drawing more power, getting shorter lifetime of those fans, and it's going to be noisier. So this kind of shows it a little bit. Noise also is logarithmic to the speed of the fan. So if you were to shut off, if you had 8 fans, you shut off 4 of them, you saved 3 decibels. If you speed control all 8 fans down to 50% speed, you save 15 decibels. So it's a 12 decibel sound savings. You're still getting the same airflow. You're now at lower power, and you're going to get longer life out of all 8 of those fans. So it's something to keep in mind. Now, one of the reasons AC VFD, it might make sense to do this staging and turning on and off, like maybe you turn off one of them and keep the others high, because at 50% speed, we saw there's a big efficiency gap. So they don't want to run at 50% speed because there's inefficiencies there. They want to keep those fans running at the higher speeds as much as possible in order to keep that efficiency high. But with the EC motor, you don't have to. Now you're going to get the benefits of lower acoustics, longer life, lower power. So in summary, EC fan holds its efficiency much better, just the technology-wise, at lower speeds. It's also going to offer you an acoustic and reliability benefit. And this is on top of the space savings we already talked about, the weight savings, ease of installation that the EC fans already offer. So getting into some rumors and myths, EC motors have a higher capital cost. I think everybody in this room has heard it. And I say that's true, but it's misleading. Because the motor itself, yeah, it's more expensive. But if you take into account everything that goes into that air handler, the wiring, the belts, the time, and also the space that you can save, the casing of an air handler is not cheap. So if you could shorten that air handler, that's a major cost savings coming out from the metal of the casing. So what we found is, in general, an EC fan array will end up cheaper than an AC motor with a VFD, unless, like the example, you're using one VFD to control 24 fans, then yeah, the price does work out very, very well there for an AC motor with a VFD. But if you're looking at smaller arrays like the ones behind us, it's going to work out to be lower cost for an EC solution. EC motors don't have enough torque to overcome high static pressure systems. So this is another one. It's false, but I understand why they said this, because 10 years ago, it's right. EC fans really didn't have high static capabilities. We maxed out probably around 5-6 inches of pressure. That's not the case anymore. So we have kilowatt ranges up to 14 kilowatt, even higher than that in some cases if you have a specialty product, but they can achieve over 10 inches of static pressure now. Fairly reliably, we have a few products that can do it. So the lower or the high static applications are no longer really a limitation for EC product like it used to be. EC motors can generate incredible harmonic distortion, up to 120%. Okay, so this one I say mostly false. The reason I say it, I work for EBM Pabst. I don't know every EC motor that's in the market. Maybe some of them do generate 120% harmonic distortion. Maybe some of the ones from Asia, I don't know. But I could tell you, ours isn't going to be generating 120%. Full load, ours is normally around 30 to 35%. This is going to be fine for most buildings. Hospitals, lots of times, require low harmonics. Sometimes there might be states that require low harmonics in their government buildings. For that, we have external filters that you can use. We have some really good partners that have designed some filters for us. That'll get you to about a little less than 5% harmonic distortion at full load. And then we also have active filters built into the back of them on some of our product. So if you use that, you'd get to about under 2% harmonic distortion at full load, and it'll actually hold that pretty much down to 30% load. It'll be below 5%. EC motors can't ride through power dip situations. So this one's just false. We have a really wide voltage range. We have a 10% tolerance on the voltage range. So it's a substantial range that these EC motors can run at. And then EC motors can't catch a spinning load, something that's critical in the HVAC industry. Also false. So our fans, I mentioned that braking feature that's in the fan. And another thing that it will do is, say that the power left the fan and it starts spinning down, but it's not at rest yet, and power is restored. The EC fan will actually recognize what it's spinning at and ramp up from that point. So you don't have to worry about it over-ramping, overdriving, anything like that. The fan's pretty smart. It could tell you exactly where it was running and it knows exactly what to do to get back up to full speed. Also, this video might be a little tough to see, but what this one shows, I could just describe it. So I mentioned that brake that's built into the fan. This is a condenser fan, though. Let's say that you're on the top of a roof and the wind's blowing really strong and the fan's now spinning in the wrong direction. And that condenser's off and you want to turn it on. With the AC fan, you won't be able to turn it on, right? Because it's spinning in the wrong direction. It can't actually torque up and spin the right direction. The EC fan will actually notice it's spinning wrong when the power is applied, apply the brake, so it'll go to a stop, and then it will ramp up the speed from there. EC fans cannot be connected directly to field bus networks like BACnet. Matt already told you that one's false, because obviously Q-PAC has been doing it for quite some time now. So I say it's true but misleading, because yes, normally it needs to be integrated through something, but it is possible. BACnet is not a problem with the EC fans. EC motors cannot program to perform PID control. This one, I honestly don't even know where the person got that, because it's in our literature that we have built-in PID control. And the last one, EC motors have extremely long lead times, have to come from Europe. As I already mentioned, that one's false. That's our production facility in Tennessee. So 177,000 square foot facility, pumping out motors. It's been open for about a year now, fully in production. So very, very exciting for us. I'll tell you another story. I started at EBM 12 and a half years ago. And my first day on the job, I asked our VP of engineering, are we ever going to make these motors in the US? And he said, no, we're a German company. They're never going to let us make motors in the US. And it was one of the most interesting things to see how much in 12 years our mindset has shifted from being just a German company to truly a global company, and US production really driving us in the future. So very exciting. And that's it. So yeah, if you guys have any questions. Sure, so you do need fusing or breakers, but you don't need specific SCCR calculations included into it. So you would just be factoring in the if you looked at the full load amps, you would give it the buffer on the breaker on the fuses, and that's all you need to really calculate. So it's just a simpler design. Yes?
That if a facility owner has a whole bunch of the same fan, that they could keep one as spare, right? But I've heard that you shouldn't keep one as spare, because with a certain storage time, you start to have bearings getting flattened and other stuff. Could you explain what the balance is there? What are the detriments of keeping a spare unit, and what makes it okay?
Sure. So you are right that the bearing grease will get loaded to one side if it's just kept there for too long. But the way to alleviate that is to actually just have a plan where every 6 months you either power it quick and just for like 5 minutes just to get the bearing, the grease redistributed through the bearing. You can have it manually spun for a while just to redo the grease, essentially. That's the key part, is just keeping that grease even throughout it. One other thing I wanted to mention is when we're talking about replacement, I've been talking about bearings as kind of being the major issue, major failure point. That's kind of what dictates the life. But we all know things get wired wrong in the field. There's electrical problems, there's lightning strikes. So if on our new motors, when there is an electrical problem, like something was wired wrong or it got an overvoltage somehow, the electronics on the back of it are replaceable. So you don't need to buy a whole new motor in that case. It's just a Lego piece. 6 screws pop off, you put the new electronics on, and you're done. Yes. Yeah, so that's the active PFC option. So that's integrated into the back of the electronics. That's not available on all sizes. So you would need to make sure that you're in the size range that it's applicable for. But any size could use a passive filter on the outside. So you would just buy, and in that case, you'd be buying one filter for the bank of fans. You wouldn't be doing it at a fan level. It'd be on a system level. Yep. As far as replacing the electronics, I honestly don't know the answer, but the other groups are here today, so I'd recommend asking them if what their replacement is on electronics. Yes.
Why do you not have a greasable bearing?
Because the whole idea of it is to be maintenance free. So the ideal situation is you just plug it in and you never have to do anything throughout the service life. The bearings are also inside of the rotor, so it makes it very, very difficult to access those bearings. So part of it's because of design and part of it's because it's meant to be truly maintenance free.
If it kills the electronics, is there a way to make sure that it didn't go through the electronics down to the stator itself? Or, because if you replace just that, normally, at least in the older generations of electronics, you'd have special tooling to make sure that the Hall effect sensors were still good. So I just want to make sure we just
Yes. So the new version of the electronics does not have a Hall effect sensor, which is part of it. So that's one of the reasons we're not as worried about it. You still would want to just do some resistance checks on the windings, make sure that nothing really has damaged the coatings on the windings. But it's a simpler check, and like I said, there's no Hall effect sensors going into the motor, so you don't have to worry about that. Hall effect sensor it's just something that measures the speed of the fan. So it tells you how many rotations per minute, and it actually tells you how many pulses per minute, and then or per rotation, and then you divide it, and then you get the speed. Yep.
Any concerns with humidifier placement regarding the fans?
So as far as being in a humid environment, or I don't think I understand that question.
Are they fully sealed? Like, is there any concern about having a humidifier directly upstream of these fans with all the electronics built into them?
The electronics are fully sealed, so you don't have to worry about the electronic side. The fans are normally rated. We have fans rated for all different humidities. So some of these fans are rated to, like that condenser fan I showed the video of, that's rated to be outdoor 24/7. So in rain, in very, very high humid condensing environments, that's fine. In an air handler, normally I think we can get up to like 98% humidity. So it's fine to be in a humid environment, as long as normally you don't want too much condensation in an air handler, but the fan itself can handle it.
What about steam or heat rating?
So every fan is going to have a max ambient temperature rating, and that'll tell you right away, hey, that'll tell you what the ambient temperature needs, what range it needs to be in. They do vary by fan, so it's no set range, but every fan has it clearly marked what the max ambient temperature is.
I just want to comment on the living life of these fans. They live in a saturated environment, and here in Florida, what we've noticed over time is that those fan arrays will develop like a black growth, both on the wheel, motor, electronics, pretty much anything that's saturated in that environment. It's a little unsightly. We're not really sure what it is. We've never had it analyzed, but it appears to be some sort of microbial growth that begins to form, and that's black in color. So we've seen that happen over and over again, especially on Q-PAC arrays that are older than 5 years. So if you ever see it, that's what's happening, is it's operating in that saturated environment, for a long time. And it's dark, and it's wet, and it's cold. So just understand that can happen.
Yeah. To me, that sounds more of a maintenance concern of, hey, maybe once a year you turn the unit off for a little bit and wipe it clean. I think that's probably something that's easily solved with a maintenance routine. Yes. So the wheels that we're selling into this market are aluminum, so there's no concern with UV light.
On UV light, what about so the backs of those, like the plastic casing and the cover and all that, are those UV rated? I can only speak to ours because I know ours. Ours are UV rated because they are meant to be out in the sun in the environment. So they are UV rated. If there are any specific concerns about a specific type of UV light used for UVC, we could take a look at that specifically. I know that we've already investigated it, so that's something that we could definitely get back to you on. But UVC, I know, is a concern with some plastics. I think the electronics cover on ours is okay, but I'm not 100% sure.
Okay. Kind of in that same vein of the UVs, what about ionizers, the induct ionizers? Does that affect any part of the motor when you've got a customer that's installed those across their system?
I do not believe it does because I know we are installed with ionizers. I don't know if there's a special protection we need to put on, because lots of times when we're selling something to a customer that needs something specific, we might do a coating.
But I don't believe there's any concern with our standard product. I know it goes into ionizers, so it's something that the EC fan can definitely handle. But if that's a specific unit, it's definitely worth asking the question to our engineering team just to confirm that the standard product has no problem. Anybody else? We good? All right. Thank you guys all very much.